Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Deep beneath a mountain in Japan, scientists huddle around computer screens displaying data that could rewrite our understanding of the sun. They're not looking at light. They're hunting for something far more elusive: neutrinos. These ghostly particles pass through your body at a rate of 100 billion per second, yet you never feel them. They're the universe's most abundant messengers, carrying secrets from the heart of stars across billions of miles without interference. Neutrinos were first theorized in 1930 by Wolfgang Pauli, who needed them to explain missing energy in radioactive decay. For 26 years, they remained purely theoretical. Then in 1956, Frederick Rains and Clyde Cowan finally detected these phantom particles using a nuclear reactor and massive tanks of water. Their discovery earned them the Nobel Prize and opened an entirely new window into the cosmos. The sun produces neutrinos through nuclear fusion in its core, where temperatures reach 15 million degrees Celsius. Every second, 600 trillion neutrinos leave the sun in all directions. Unlike light, which takes thousands of years to escape the sun's dense interior, neutrinos zip straight through in just 2 seconds. They arrive at Earth carrying pristine information about nuclear reactions happening right now in the solar core. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. But here's the challenge. Neutrinos barely interact with matter. A neutrino could pass through a light year of lead. That's 6 trillion miles, and have only a 50% chance of hitting a single atom. This makes them incredibly difficult to detect despite their abundance. To catch even a handful, scientists must build enormous underground detectors, filled with thousands of tons of ultra-pure water or liquid scintillator. The race to decode solar neutrinos began in the 1960s with Raymond Davis Jr.'s pioneering experiment in the Homestake gold mine in South Dakota. Davis used 600 tons of dry cleaning fluid, tetrachloroethylene, buried 1 mile underground to shield it from cosmic rays. When a neutrino occasionally struck a chlorine atom, it would transform into radioactive argon, which Davis could detect. His results shocked the scientific community. He found only 1/3 of the expected neutrinos. This discrepancy, known as the solar neutrino problem, plagued physics for 30 years. Either our understanding of the sun was wrong, or neutrinos were more mysterious than anyone imagined. The answer would require a new generation of detectors and a revolution in particle physics. Today's neutrino observatories are marvels of engineering. Super Kamiokande in Japan sits in a zinc mine 1,000 meters underground, containing 50,000 tons of ultra-pure water, watched by 11,000 photomultiplier tubes. The Sudbury Neutrino Observatory in Canada uses 1,000 tons of heavy water to catch neutrinos through 3 different detection methods. These facilities operate like cosmic archaeologists, sifting through trillions of particles to find the rare neutrino interactions that reveal the sun's secrets. Modern detectors can distinguish between different types of neutrinos and measure their energies with unprecedented precision. Scientists have discovered that neutrinos change flavor as they travel, a phenomenon called neutrino oscillation that solved the solar neutrino problem and earned multiple Nobel Prizes. This discovery not only vindicated our understanding of stellar physics, but revealed that neutrinos have mass, fundamentally changing our picture of particle physics and cosmology. The messages carried by solar neutrinos are more valuable than gold. They provide real-time information about nuclear fusion rates, core temperature, and internal structure of our nearest star. As we stand on the brink of a new era in neutrino astronomy, these invisible messengers promise to unlock mysteries about stellar evolution, dark matter, and the fundamental nature of the universe itself. 2 kilometers beneath the Gran Sasso mountain in Italy, engineers are constructing what might be humanity's most ambitious scientific instrument. The Deep Underground Neutrino Experiment, or DUNE, will eventually house 40,000 tons of liquid argon in chambers the size of cathedral naves. This underground realm represents the cutting edge of neutrino detection technology, where scientists push the boundaries of engineering to catch particles that barely acknowledge the existence of matter. The challenge of building underground neutrino detectors begins with location. Scientists need sites deep enough to block cosmic rays, high-energy particles from space that would overwhelm sensitive detectors. The ideal depth is between 1 and 2 kilometers underground, equivalent to being under 3 to 6,000 meters of water. This cosmic ray shielding is so critical that every major neutrino observatory is buried. Super Kamiokande under Mount Ikano in Japan, ICE Cube at the South Pole, and SNOLAB in Canada's Creighton mine. Construction requires unprecedented precision and cleanliness. At Super Kamiokande, workers spent years polishing the interior walls of a cylindrical cavern, 40 meters tall and 40 meters wide. They installed 11,200 photomultiplier tubes, devices that can detect single photons, arranged in a perfect geodesic pattern. Each tube costs as much as a luxury car and must be calibrated to nanosecond precision. The entire detector holds 50,000 tons of water so pure it would be considered toxic to drink, lacking the minerals necessary for human survival. The Sudbury Neutrino Observatory, or SNO, took cleanliness to extraordinary levels. Scientists used only ultra-low radioactivity materials, screening every component for trace amounts of natural uranium, thorium, and radium. Even the stainless steel came from specific foundries that could guarantee minimal radioactive contamination. Workers wore special clothing and followed protocols stricter than those in semiconductor manufacturing. A single speck of radioactive dust could compromise years of data collection. Liquid argon detectors, like those planned for DUNE, present unique engineering challenges. Argon must be cooled to minus 186 degrees Celsius to remain liquid, requiring massive cryogenic systems operating continuously for decades. The liquid must be ultra-pure, with impurities measured in parts per trillion. Even trace amounts of oxygen or water would absorb the faint light signals produced by neutrino interactions, rendering the detector blind. The electronics inside these detectors represent miracles of miniaturization and radiation hardness. Thousands of sensors must operate reliably for years in extreme conditions, underground, in cryogenic temperatures, surrounded by ultra-pure liquids that would corrode standard materials. Signal processing requires distinguishing genuine neutrino events from radioactive decay, cosmic ray muons that penetrate the shielding, and electronic noise, a challenge comparable to hearing a whisper in a thunderstorm. Data acquisition systems handle enormous volumes of information. Super Kamiokande generates terabytes of data annually, with computers analyzing every photon detected by the 11,000 photomultiplier tubes. Machine learning algorithms trained on simulated neutrino interactions help identify the subtle patterns that distinguish neutrino events from background noise. The analysis requires understanding detector response so precisely that scientists can reconstruct the energy and direction of neutrinos from patterns of light lasting mere microseconds. International collaboration drives these projects. DUNE involves over 1,000 scientists from 35 countries, sharing expertise in particle physics, cryogenics, electronics, and data analysis. The Hyper Kamiokande project, planned as Super Kamiokande's successor, will be 8 times larger and require unprecedented international coordination. These collaborations represent modern science at its best, diverse teams united by curiosity about fundamental questions. The cost of neutrino detection reflects its technical demands. Super Kamiokande cost $100 million in 1996 dollars. DUNE's total budget exceeds $3 billion, spread over 25 years of construction and operation. Yet these investments pale compared to the knowledge gained. Understanding stellar nucleosynthesis, probing physics beyond the standard model, and potentially discovering new particles or forces that could revolutionize technology. These underground cathedrals of science represent humanity's determination to understand the invisible universe. Every photomultiplier tube, every ton of ultra-pure liquid, every line of analysis code serves a single purpose: catching nature's most elusive messengers and decoding their cosmic secrets. At the center of our Sun, 15 million degrees Celsius and crushing pressure, 250 billion times greater than Earth's atmosphere, create conditions so extreme that the fundamental forces of nature bend to stellar will. Here, in a sphere smaller than Earth but containing half the Sun's mass, hydrogen nuclei overcome their mutual electrical repulsion and fuse into helium. This process, called the proton-proton chain, transforms 4 million tons of matter into pure energy every second and produces the neutrino messengers that travel directly to Earth. The proton-proton chain begins when two hydrogen nuclei, single protons, collide with enough energy to overcome the electromagnetic force that normally keeps them apart. In the intense heat and pressure of the solar core, protons reach speeds of 600 kilometers per second. Even so, quantum mechanics makes fusion improbable. Only one collision in 10 billion results in fusion. The Sun compensates through sheer scale, containing 10 to the power of 57 protons, undergoing constant collisions. When fusion succeeds, one proton transforms into a neutron through beta plus decay, releasing a positron and a neutrino. This process, mediated by the weak nuclear force, occurs in less than 1 second, but requires precise quantum mechanical tunneling. The newly formed deuteron, a nucleus containing one proton and one neutron, quickly fuses with another proton to create helium-3 and a gamma ray. Two helium-3 nuclei then collide to form helium-4, releasing two protons back into the stellar cauldron. Each complete fusion cycle converts 658 million electron volts of mass into energy, following Einstein's famous equation E equals mc squared. 98% becomes gamma rays that begin the 1,000-year journey through the Sun's dense interior, bouncing between atoms in a random walk toward the surface. But 2% escapes immediately as neutrinos, carrying information about the nuclear furnace directly to Earth at the speed of light. The Sun produces 3 types of neutrinos through different fusion pathways. Proton-proton neutrinos, the most abundant, carry relatively low energy, up to 420,000 electron volts. Boron-8 neutrinos, produced in a rare branch of the fusion chain, carry higher energies up to 15 million electron volts but are 10,000 times less common. Beryllium-7 neutrinos occupy the middle ground, with discrete energies of 862,000 electron volts. These energy signatures act like cosmic fingerprints, allowing scientists to probe different aspects of solar physics. Low-energy proton-proton neutrinos reveal the basic fusion rate and solar luminosity. High-energy boron-8 neutrinos are sensitive to core temperature, providing thermometers for the solar interior. The ratio between different neutrino types tests theoretical models of stellar nucleosynthesis with unprecedented precision. The solar neutrino spectrum carries information impossible to obtain through any other means. Light from the Sun's surface tells us about conditions thousands of years ago, when those photons began their journey from the core. Solar neutrinos arrive within 8 minutes of their creation, providing real-time monitoring of nuclear fusion. This temporal advantage makes neutrino astronomy invaluable for studying stellar variability and internal dynamics. Standard solar model calculations predict neutrino production rates with remarkable precision, incorporating quantum mechanics, thermodynamics, and nuclear physics. These models match observed solar properties, luminosity, mass, composition, and oscillation frequencies, to within 1% accuracy. Neutrino detection tests these models at the most fundamental level, verifying our understanding of stellar physics and nuclear reactions. Recent measurements reveal subtle variations in solar neutrino flux correlated with solar magnetic activity. During solar maximum, when sunspot numbers peak, neutrino detectors observe slight increases in high-energy neutrino rates. These variations, though small, suggest connections between surface magnetic phenomena and core nuclear processes that theoretical models are still working to explain. The precision of modern neutrino measurements has transformed solar physics from descriptive to predictive science. Scientists can now calculate fusion rates, energy generation, and stellar evolution with confidence backed by direct observation of the nuclear processes. This capability extends beyond our Sun. Understanding stellar neutrino production helps astronomers model other stars, predict supernova explosions, and trace the cosmic history of element formation. Every neutrino detection is simultaneously a measurement of distant nuclear physics and a test of fundamental particle properties. The Sun serves as a natural laboratory operating at energies and scales impossible to reproduce on Earth, broadcasting its secrets through neutrino messengers that carry information across 93 million miles in just 8 minutes. In 1968, Raymond Davis Jr. published results that would haunt physics for 3 decades. His pioneering experiment in the home state gold mine detected only 1/3 of the solar neutrinos predicted by theoretical models. This wasn't a small discrepancy that could be explained by measurement uncertainty. It was a factor of 3 deficit that challenged our fundamental understanding of either stellar physics or particle properties. The solar neutrino problem had begun. Davis's detector was elegantly simple in concept, but fiendishly difficult in execution. 615 tons of perchloroethylene, common dry cleaning fluid, sat in a tank the size of an Olympic swimming pool, 1 mile underground in an abandoned gold mine. When a solar neutrino struck a chlorine-37 nucleus, it would occasionally transform it into radioactive argon-37. Davis would then extract this argon using helium gas and count individual radioactive decays in proportional counters. The expected rate, calculated from standard solar model predictions and known nuclear cross-sections, was about 1 argon atom produced per day. Davis typically found only 1 argon atom every 3 days, a persistent, inexplicable deficit. Critics initially suspected experimental errors, radioactive contamination, incomplete argon extraction, or cosmic ray interference. But Davis's meticulous procedures withstood scrutiny. After 20 years of operation, his results remained stubbornly consistent with detecting only 33% of theoretical predictions. The implications were profound and troubling. Either the Sun wasn't shining through nuclear fusion, contradicting centuries of stellar astronomy, or neutrinos possessed unknown properties that theoretical physics hadn't accounted for. Both possibilities threatened established science. Solar models had successfully explained stellar luminosity, lifetime, and internal structure. Particle physics had incorporated neutrinos as massless, unchanging entities since the 1930s. Soviet physicist Bruno Pontecorvo had proposed a radical solution in 1957, neutrino oscillations. If neutrinos could change between different types during their journey from the Sun to Earth, detectors sensitive to only one type would observe apparent deficits. This required neutrinos to have mass, violating the standard model of particle physics. Most physicists considered oscillations an exotic possibility with little experimental support. The mystery deepened with new experiments using different detection methods. The Kamiokande detector in Japan used ultra-pure water to detect high-energy neutrinos through Cherenkov radiation, the blue glow produced when particles travel faster than light in water. Kamiokande confirmed Davis's deficit for the high-energy portion of the solar neutrino spectrum. The SAGE and GALEX experiments in Russia and Italy used gallium instead of chlorine, targeting lower-energy neutrinos. They too found deficits, though smaller than Davis's results. 3 different experiments using 3 different elements, chlorine, water, and gallium, all observed fewer neutrinos than predicted. The pattern suggested the deficit wasn't experimental error but genuine physics. Yet the deficits varied with neutrino energy, creating a puzzle within the puzzle. High-energy boron-8 neutrinos showed the largest deficit, while lower-energy neutrinos showed smaller but still significant shortfalls. Theoretical physicists proposed increasingly exotic solutions. Maybe the Sun's core temperature was lower than calculated, reducing high-energy neutrino production. Perhaps unknown particles called axions were stealing energy from the solar interior. Some suggested modifications to gravity or electromagnetism in extreme conditions. Each proposal faced difficulties explaining either solar observations or laboratory measurements. The solar neutrino problem created a crisis of confidence in fundamental physics. Textbooks hedged their statements about stellar nucleosynthesis and neutrino properties. Graduate students learned about this unsolved puzzle as a prime example of how observations could contradict well-established theory. The problem became a touchstone for discussions about scientific method. How do we proceed when reliable experiments disagree with successful theories? Experimentalists responded by building larger, more sophisticated detectors. Super Kamiokande, 50 times larger than its predecessor, could measure neutrino energies and arrival directions with unprecedented precision. The Sudbury Neutrino Observatory used heavy water to detect neutrinos through 3 different nuclear reactions, providing multiple measurements from a single detector. These new facilities promised to either confirm the deficit or reveal systematic errors in earlier experiments. The stakes extended beyond solar physics. Neutrino properties affect cosmology, determining how matter clumped in the early universe. If neutrinos had mass and could oscillate, the implications would ripple through particle physics, astrophysics, and our understanding of fundamental forces. The solar neutrino problem wasn't just about missing particles, it was about missing pieces of reality itself. By the late 1990s, 3 decades of careful measurements had established the deficit beyond reasonable doubt. The question was no longer whether neutrinos were missing, but why. The answer would require rethinking some of physics' most basic assumptions about these ghostly messengers from the sun. On June 18, 2001, scientists at the Sudbury Neutrino Observatory made an announcement that would revolutionize physics. After 5 years of operation 2 kilometers underground in Ontario, Canada, SNO had solved the solar neutrino problem. The missing neutrinos weren't missing. They were changing identity during their 8-minute journey from the Sun to Earth. This discovery of neutrino oscillations would earn the Nobel Prize and fundamentally alter our understanding of particle physics. The breakthrough came from SNO's unique design using 1,000 tons of heavy water, deuterium oxide, borrowed from Atomic Energy of Canada Limited at a cost of $300 million. Unlike previous experiments that could detect only electron neutrinos, SNO could observe all 3 neutrino types, electron, muon, and tau neutrinos. This capability would prove crucial for solving the 30-year-old mystery SNO employed 3 detection methods simultaneously. The charged current interaction occurred when electron neutrinos struck deuterium nuclei, breaking them apart and producing easily detectable electrons. The neutral current interaction happened when any type of neutrino hit deuterium, releasing neutrons that could be captured and counted. The elastic scattering interaction involved neutrinos bouncing off electrons, creating characteristic light patterns in the detector. The charged current measurement confirmed previous experiments. SNO detected only about 1/3 of the electron neutrinos predicted by solar models, but the neutral current measurement revealed the missing piece of the puzzle. When counting all neutrino types together, SNO observed exactly the number predicted by theoretical calculations. The total neutrino flux matched expectations perfectly. Only the distribution among neutrino types had changed. This pattern could only be explained by neutrino oscillations. Electron neutrinos produced in the Sun's core were transforming into muon and tau neutrinos during their journey to Earth. Previous experiments had detected the deficit because they were sensitive primarily to electron neutrinos. The neutrinos weren't disappearing, they were changing costume en route. Neutrino oscillations required 2 revolutionary insights. First, neutrinos must have mass. The standard model of particle physics had assumed neutrinos were massless, like photons. Mass, differences between neutrino types, drive oscillations through quantum mechanical interference effects. Second, the 3 neutrino types must mix quantum mechanically, similar to how quantum particles can exist in superposition states. The mathematics of neutrino oscillations involve probability waves oscillating at different frequencies as neutrinos travel. The oscillation length, the distance over which neutrinos cycle between types, depends on their mass differences and energies. For solar neutrinos, the oscillation length spans millions of kilometers, making the Sun-Earth distance ideal for observing these quantum mechanical transformations. Super Kamiokande provided crucial supporting evidence through atmospheric neutrino studies. Cosmic rays hitting Earth's atmosphere produce neutrinos that travel different distances depending on whether they approach from above or below the detector. Muon neutrinos traveling through the entire Earth showed significant deficits compared to those arriving from directly overhead, confirming oscillations over terrestrial distances. The discovery required unprecedented precision in both theory and experiment. Solar model calculations had to account for neutrino production rates, energy spectra, and interaction cross-sections with accuracies of a few percent. Detector calibration involved understanding light propagation through thousands of tons of ultra-pure heavy water, photo-multiplier tube responses, and background contamination from natural radioactivity. Neutrino oscillation parameters, the mixing, angles and mass differences that govern flavor changes, emerged from combined analysis of solar, atmospheric, reactor, and accelerator neutrino experiments. The large mixing angle solution explained solar neutrino data, with electron neutrinos having roughly 50% probability of transforming during their journey from the Sun's core to Earth's surface. The implications extended far beyond solving the solar neutrino problem. Neutrino masses affect cosmological structure formation, contributing to dark matter and influencing galaxy evolution. Oscillations provide a window into physics beyond the standard model, suggesting new symmetries and interaction mechanisms. The discovery opened entirely new research directions in particle physics and astrophysics. Technological advances made the discovery possible. Low background detector construction, ultra-pure material production, and sophisticated electronics all required pushing engineering capabilities to their limits. The success demonstrated how fundamental physics drives technological innovation, with techniques developed for neutrino detection finding applications in medical imaging, nuclear monitoring, and materials science. The solar neutrino problem had transformed from crisis to triumph. What appeared to be a fundamental contradiction between theory and observation revealed new physics more subtle and beautiful than anyone had imagined. Neutrinos, the universe's most elusive particles, had taught humanity that nature's deepest truths often hide in the most unexpected places. The discovery of neutrino oscillations launched a golden age of neutrino astronomy. Today's detectors routinely monitor the Sun's nuclear furnace in real time, providing instantaneous readings of fusion rates 15 million kilometers beneath the solar surface. This capability has transformed neutrino detection from a decades-long struggle to catch a few dozen particles into a precise astronomical tool that observes thousands of neutrino interactions annually. Modern neutrino observatories operate with sensitivity unimaginable during the solar neutrino problem era. Super Kamiokande, after upgrades completed in 2018, detects approximately 15 solar neutrino events daily with energy and directional information for each interaction. The Borexino experiment in Italy's Gran Sasso laboratory has achieved even more remarkable precision, measuring individual components of the solar neutrino spectrum with unprecedented accuracy. Borexino's achievement represents the pinnacle of low background detector technology. Its 300 tons of liquid scintillator are so pure that radioactive contamination measures in parts per quadrillion, equivalent to finding a single grain of sand in all the world's beaches. This extraordinary cleanliness allows detection of the lowest energy solar neutrinos, those produced directly by proton-proton fusion reactions that power the Sun. Real-time solar monitoring through neutrinos provides capabilities unavailable through any other observational method. While solar telescopes observe light that began its journey from the core thousands of years ago, neutrino detectors see nuclear reactions happening right now. This temporal advantage allows astronomers to study solar variability on timescales, from minutes to decades, searching for connections between core fusion rates and surface phenomena. Scientists have used this capability to test exotic theories about solar behavior. Some models predicted that solar luminosity might vary by small amounts over time, driven by changes in core composition or magnetic field effects on nuclear reaction rates. Decade-long neutrino observations have constrained such variations to less than 2%, confirming the Sun's remarkable stability as a nuclear reactor. The precision of modern measurements has revealed subtle correlations between solar neutrino flux and the 11-year solar magnetic cycle. During periods of maximum sunspot activity, detectors observe slight increases in high-energy neutrino production, suggesting possible connections between surface magnetism and core nuclear processes. These variations, while small, provide new insights into the Sun's internal dynamics. Next-generation detectors promise even greater capabilities. The Jiangmen Underground Neutrino Observatory, or JUNO, under construction in China, will contain 20,000 tons of liquid scintillator. Surrounded by 17,000 photomultiplier tubes, this facility will measure solar neutrino oscillation parameters with precision sufficient to determine the absolute neutrino mass scale, information crucial for cosmology and particle physics. Hyper Kamiokande, planned as Super Kamiokande's successor, will hold 260,000 tons of ultra-pure water, 5 times larger than any existing detector. This enormous volume will enable statistical studies impossible with current facilities, potentially revealing rare neutrino interactions or subtle variations in solar neutrino production that smaller detectors cannot observe. The Deep Underground Neutrino Experiment plans to extend neutrino astronomy beyond the Sun. DUNE's massive liquid argon detectors will be sensitive to neutrinos from supernovae throughout our galaxy, potentially detecting thousands of events from a single stellar explosion. This capability would provide unprecedented insights into core collapse physics and neutron star formation. Modern neutrino astronomy has also opened new frontiers in fundamental physics. Precise measurements of solar neutrino oscillations constrain theories of physics beyond the Standard Model, searching for additional neutrino types, new interactions, or modifications to known forces. These studies use the Sun as a natural laboratory, operating at energies and scales impossible to reproduce on Earth. Machine learning techniques have revolutionized neutrino data analysis. Neural networks trained on simulated detector responses can identify neutrino interactions with efficiency exceeding 95%, distinguishing genuine events from radioactive background with superhuman accuracy. These algorithms enable real-time analysis of detector data, providing immediate alerts for unusual neutrino signatures. International collaboration drives the field forward. The Global Neutrino Network coordinates observations between detectors worldwide, enabling coincident searches for transient phenomena and combined analyses that achieve precision impossible for individual experiments. This cooperation demonstrates how modern science transcends national boundaries in pursuit of fundamental knowledge. Solar neutrino astronomy has matured from solving a troubling puzzle to becoming a precision tool for studying stellar physics, particle properties, and cosmological questions. The Sun's constant stream of neutrino messengers provides a laboratory for fundamental physics that operates 24 hours a day, 7 days a week, broadcasting nature's secrets to anyone with the technology and patience to listen. The future of neutrino astronomy stretches toward discoveries that would have seemed impossible during the early days of the solar neutrino problem. Scientists are developing technologies to detect individual neutrino interactions with unprecedented precision, build detectors the size of small cities, and potentially decode neutrino messages from the most violent events in the universe. These advances promise to transform our understanding of stars, galaxies, and the fundamental nature of reality itself. The 30-meter telescope and extremely large telescope will revolutionize optical astronomy, but neutrino astronomy's future lies underground and underwater. The proposed Pacific Ocean Neutrino Experiment, or PONE, would deploy thousands of light sensors across cubic kilometers of seawater, creating a detector volume larger than Manhattan. This facility would capture neutrinos from active galactic nuclei, gamma-ray bursts, and other cosmic phenomena invisible to conventional telescopes. Quantum sensors represent the next frontier in neutrino detection technology. Researchers are developing superconducting devices cooled to mere thousandths of a degree above absolute zero, where quantum mechanical effects enable detection of individual neutrino interactions with unprecedented sensitivity. These devices could distinguish between different neutrino types in real time, measuring properties that current detectors can only determine through statistical analysis of thousands of events. The coherent elastic neutrino nucleus scattering process, predicted theoretically but only recently observed, opens new possibilities for compact neutrino detectors. This interaction allows much smaller devices to detect neutrinos efficiently, potentially enabling portable neutrino telescopes that could monitor nuclear reactors, search for supernova explosions, or study geological processes through underground neutrino tomography. Artificial intelligence will revolutionize neutrino data analysis over the next decade. Deep learning networks are already demonstrating capabilities that exceed human pattern recognition, identifying subtle signatures in detector data that human analysts might miss. Future AI systems will operate as autonomous astronomers, continuously monitoring neutrino streams for unexpected phenomena and alerting human scientists to potential discoveries in real time. The search for sterile neutrinos, hypothetical particles that interact only through gravity, represents one of the most exciting frontiers in particle physics. These particles could help explain dark matter, cosmic ray anomalies, and the matter-antimatter asymmetry of the universe. Next-generation experiments will search for sterile neutrino signatures in solar neutrino oscillations, with sensitivity sufficient to confirm or rule out their existence definitively. Multi-messenger astronomy, combining neutrinos with gravitational, waves, gamma rays, and optical observations, will become routine within the next 20 years. When neutron stars collide or black holes consume matter, they produce distinctive signatures across multiple channels. Coordinated observations will provide complete pictures of these extreme events, revealing physics impossible to study through any single observational method. The proposed Darwin mission concept would place neutrino detectors throughout the solar system, using the Sun as a cosmic lighthouse to study neutrino propagation across different distances and gravitational fields. Detectors near Mercury would observe neutrinos after traveling 58 million kilometers, while those near Neptune would catch neutrinos after journeys of 4.5 billion kilometers, testing fundamental physics across unprecedented scales. Breakthrough technologies under development could shrink neutrino detectors from cathedral-sized installations to tabletop devices. Metamaterials with engineered properties not found in nature might enhance neutrino interaction rates by orders of magnitude. Quantum coherent detection schemes could amplify weak neutrino signals through constructive interference, making detection possible with much smaller detector masses. The long-term vision includes neutrino communication systems for interstellar exploration. Unlike electromagnetic signals, neutrinos travel unimpeded through planets, stars, and interstellar gas. Future space missions could use modulated neutrino beams to maintain communication with Earth even when blocked by stellar objects, enabling exploration of the outer solar system and eventually nearby star systems. Neutrino archaeology will reconstruct the Sun's history through isotopic analysis of ancient materials. Different fusion processes in the solar core produce distinctive neutrino signatures that could be preserved in meteorites or lunar samples. By analyzing these fossil neutrino records, scientists could study how solar neutrino production has varied over billions of years, providing insights into stellar evolution and early solar system conditions. The ultimate goal is understanding neutrinos' role in cosmic evolution. These particles carry information from the universe's first 3 minutes after the Big Bang, when primordial nucleosynthesis created the light elements. Detecting relics. Neutrinos from this epoch would provide direct observation of conditions in the infant universe, complementing cosmic microwave background observations with particle data from the same era. Every advance in neutrino detection technology brings us closer to understanding the invisible universe. The ghostly messengers that once seemed impossible to catch now serve as precise tools for studying the most extreme conditions in nature. As we stand on the threshold of discoveries that will reshape physics and astronomy, neutrinos continue teaching us that the universe's greatest secrets often hide in its most elusive phenomena.